Welcome everybody to Algebra 2, Section 3.2, Piecewise Functions, Parent Functions, and Transformations. So let's first define what a piecewise function is. And a piecewise function, see if we can try and writing a little bit better with this. A piecewise function is made up of two or more functions, each with, that's W slash is shorthand for with, each with its own domain. This once again are the x values. And so the first 5 letters of piecewise, piece there, really emphasize what a piecewise function is, telling us that it's pieces of functions put together, or functions pieced together or put together, paired together. And so how we evaluate piecewise functions, aka plug a number in, get a number out, plug in an x, get a y out, depends on what function it is. And so this would be how a piecewise function would look. We have this brace here, similar to how when we have a system of equations. However, the rest of the setup is different. We have an f of x equals or a y equals before it, letting us know it's a function rather than a system of equations. And then also we have a rule. So we have the rest of the function, in this case x squared minus 1 or 5x plus 3. Now it would be pretty normal for us to see all of this and say f of x equals 5x plus 3. That's pretty normal, and it's pretty normal for us to see this as well. F of x equals x squared minus 1. And by seeing them together, okay, well, we have two different functions. We have this function and this function. And so the question becomes, how do we know which one to use? And after the if, or sometimes there's a comma or a semicolon instead of an if, it tells us when to use each function. And so after this, it says when x is less than -2, we plug it into this function. But when the x value is greater than or equal to -2, we plug it into the bottom function. And so, for example, when you're on letter A here, we're finding f of -5, we ask ourselves, okay, is -5 less than -2, or is it greater than or equal to -2? And the answer to that -5 is less than -2, meaning we plug it into this top function, x squared minus 1. And so we do -5 squared minus 1, and because the x is negative, it goes in parentheses here. And so then when we square that, we end up getting 25 minus 1, and so f of -5 is 24. Now we're going to move on to letter B here, and when we plug in f of -2, we have to ask ourselves once again, which of these two criteria does it meet? Is it greater than -2, or greater than or equal to -2 on the bottom, or is it less than -2 like the top? Well, -2 is equal to -2, which is the bottom one, so we plug it into 5x plus 3. And so it's 5 times -2 plus 3. And so as we continue to work this out, we end up getting -10 plus 3, and then eventually we find out that f of -2 is equal to -7. Next up here, f of 7. So once again, figuring out which criteria it meets. It does meet the criteria, the bottom one being greater than -2, and so we plug it into the bottom function, 5x plus 3, and we get 5 times 7 plus 3, which is 35 plus 3, and so f of 7 equals 38. And so once again, we determine which function to plug it into by the x value, comparing to these rules, saying which criteria does meet. We plug it into that corresponding function. So now what do we do when there's 3 parts of a piecewise function? So here there's 3 functions, and once again, each function, just like when there were 2, have their own criteria for when to plug it in. And so once again, we just figure out, okay, what criteria does meet, plug it into that corresponding function. So g of 2, well, 2 best fits in this middle one. It is greater than -4, but less than 1. So of the 3, it fits into that one, and so we get it plugged into -x minus 1. So in this case, it'd be -2 minus 1. Now notice this 2 here is positive, so only a positive 2 goes in the parentheses, but this negative is outside the x as part of the function, so it goes outside the parentheses. So now as we evaluate this one, we have negative 2 minus 1 is negative 3. So g of 2 is negative 3. On letter B here, g of negative 1, what criteria does that fit into? It fits into this middle one as well, actually, because it's also between negative 4 and 1. And so we plug it in there, and we end up getting negative of a negative 1, a negative from the negative 1, and a negative from the function itself, minus 1. So those two negatives really add, and we end up getting 1 minus 1, which is 0. So g of negative 1 is 0. Now we're going to look at letter C here, g of negative 6. Negative 6 would best fit in this top one because it is less than or equal to, in this case, less than negative 4. And so we plug it into 1 half x plus 3. And so we have 1 half times negative 6 plus 3. And 1 half times x times negative 6, or 1 half of negative 6, is negative 3. And negative 3 plus 3 is 0. So g of negative 6 is 0. And we happen to get 0 twice here, once on B and once on C. And that's perfectly fine. Now we're going to move on to graphing piecewise functions. And so in order to graph piecewise functions, what we have to do is we have to, we have to piece together the two different graphs, or later we'll say 3 different graphs, okay? I apologize for that, but my AirPod's popping up. But here we'll say, okay, well, when x is less than or equal to negative 3, so from this portion of the graph and to the left, less than or equal to negative 3, we're going to be graphing f of x equals x. However, when x is greater than negative 3, in this case, to the right of this line, but not including that line, we're going to graph this function, f of x equals negative 2x plus 1. And so we have to piece these together. And so I'll go ahead and graph this top one first. I just typically go in the order I see them. So once again, we're basing on this line here when x is negative 3. And so when x is negative 3, we're going to plug in negative 3. And what we get out as y value is just the x. So f of x equals x. And if I do f of negative 3, for example, I get negative 3 out. And so my ordered pair is negative 3 comma negative 3. And that's a closed circle because it is part of this. It is or equal to that number. So we can plug that in with a closed circle. And then I keep plugging in numbers here, for example. So I could keep plugging in like negative 4, negative 5, negative 6. Or I can look at this function and know this is y equals mx plus b. And that's just y equals 1x plus 0, for example, or with the slope of 1. And 1 over 1 you could call it as well. So it's a positive slope, so it's going uphill from left to right. So I'm going to keep going down and left for the rest of this function. Now I can't go up and right because we're told it stops when it becomes greater than negative 3. And these numbers are greater than negative 3, so we're not going to go and graph those. So we're just going to connect these from negative 3 and lower when x is less than or equal to negative 3. And so we now graph that first piece of the function. Now we're going to graph the second piece of the function down below. And so down below here, I'll do this in blue, we're going to graph this function when x is greater than negative 3. And so our first step here is to actually plug, or you could really do this anyway, but a good first step that I suggest, I should say, is to plug in negative 3 and say, okay, when you have f of negative 3, and even though it technically plugs in here to this equal sign, the reason why we'll see the reason why I want to plug this into the bottom one anyway in just a moment. So we end up getting negative 2 times negative 3 plus 1, which is 6 plus 1, or 7. Once again, I know it plugs into the top one because the top one has the or equal to and the bottom one does not. But here what's going to happen is when we have negative 3 comma 7, we're going to do an open circle there. So even though it's not actually part of the solution, that's where the graph would hypothetically get, and it's still helpful to showcase that, and it's something we do need on our graph, okay? And there are alternative ways to find that with this problem here, for example, okay? Knowing that, once again, this is y equals mx plus b, and so that's y equals negative 2x plus 1. And the m is negative 2, and the b is positive 1. And so since I know that this this bottom function is being used anywhere to the right of negative 3, which includes the y-axis, meaning we can use our y-intercept there. So I'm going to bubba bubba b again with my bubba bubba b by going up 1. And then my slope is negative 2 or negative 2 over 1, so that goes downhill from left to right. So I'm either going to go up and left, and once again, the open circle right here, which we could have found this way as well. If we didn't have it earlier, we could know what there's going to be, that's where that circle would be, but it is open because it doesn't actually equal negative 3. And then I could also go down and right from my original point that I made. Oops, sorry, try that again, down and right there. I went down 3 originally instead of down 2 like I should. And this is the second piece of the function, second piece of the graph. And so we piece the two together, the top one in the green, the bottom one in the blue, and it's just like we stitch them together, or we just kind of compare them together. And because, once again, this top function had the or equal to negative 3 has a closed circle there, where this bottom function did not, so it has an open circle there because it's not actually part of the solution. We're just saying anything greater or to the right of that open circle is part of this function. And so that is how we graph a piecewise function. So now let's talk about the domain and range of a piecewise function. So for domain, once again, it's the left and right, the x values, like we've discussed in previous lessons and last unit as well. And so how far left does this go? Well, it goes left forever. Now, we notice that it goes left forever, but it keeps going right, but then it stops here, and it picks back up here. Now, as it stops and picks back up, is there any spot where it doesn't exist? Is there any x value that's not part of this graph? And the answer is no. Every x value is still part of the graph because it still does have a part of this graph at negative 3 because it's a closed circle there, and it picks back up right after negative 3 with that open circle. So there is still an x value at negative 3 as well as everything to the left, and then it continues on to the right forever and ever and ever. Meaning this is all real numbers again, or you could also word it as negative infinity, comma infinity, because all the x values forever left and forever right are part of this. Now the range here is a little bit different. So once again, how low to how high. So this green one goes down forever, so it'd be negative infinity, but it goes up only to negative 3. Now we notice this blue one also goes down forever, and it goes up to positive 7, but not actually getting to positive 7 because it's an open circle. Now that range, they have some overlap there. They both go to negative infinity, and they both go up. This one stops much earlier than this one, and so we're going to use the one that has more overlap, saying somewhere on this graph we have the y values accounted for everywhere from negative infinity all the way up to positive 7, with not including positive 7, so it would be a parenthesis. So two ways you could word this. One, similar to the purple, would be y is less than 7, not less than or equal to though, because 7 is not part of our solution. Or you could also word it as in the interval notation, negative infinity, comma 7, with 7 having a parenthesis there. And either of those would be accurate for the range. So on number 4 here, as we turn to this, once again piecing this together, this time we're talking about on the top function being less than negative 1, so anywhere left of this line, and on the bottom function we're talking about greater than or equal to negative 1, so that line into the right of that bottom function. So I just once again typically start with the top function first and just go in order. You could really start with whichever function you want. And so as I start with this top function here, I'm going to plug in negative 1. It's kind of my typical go-to here. And I plug in negative 1, and when I do so, I end up getting the y value out, or the ordered pair, I should say, or either way, to end up being negative 4. And so I'm going to plot that, and now this time it's an open circle because negative 1 doesn't actually technically plug into this top one typically because it plugs in the bottom one because it's equal to it, and it has the or equal to. But we plug in the top one just so we know where the open circle is, very similar to what we did on the blue function, the bottom function on example 3. So now at this point, I know that my slope is -3, remembering that this is y equals mx plus b. So I'm going to use my slope to find more points. If you didn't want to use slope to find more points, you could continue plugging in numbers that are less than -1. Now I have to remember that this is going this direction for the numbers x values being less than -1. And so as I continue to go left, I go up 3 for every 1 I go left with a slope of -3/1. And so I'm going to continue to do that and continue to make these points and make my line with the arrow saying it's going forever that direction, up and to the left. Now on the bottom one, which I'll do in blue, when x is greater than or equal to -1, y equals 5. Remember, this g of x is really y, and so y equals 5. Or -5 rather. And when y equals -5, that means we plot it where y is -5, which is clear down here. And then everywhere where the y value is -5 rather, and that's just a horizontal line. Y equals a number is always a horizontal line. And because it does have the or equal to -1, it is a closed circle at -1, and it's greater than -1, meaning it's everywhere to the right of it, hence that arrow going to the right. And so now I piece together this piecewise function, I graph the two parts. And so now as I look at the domain, we look, it goes forever left, it goes forever right, and there's no break here because at least one of these, or one of them has a closed circle, so that value of -1 where the functions piece together at -1, and that we switch from one function to another, we have every x value included because we saw the x value of -1 included in this graph. And so it ends up being the all real numbers again, or you could also word it as, just like we did up above as well, in interval notation, -infinity, comma infinity, both with parentheses. These you can never reach infinity or -infinity. They're concepts, not actual numbers. Now the range here, the lowest we ever get is -5. It doesn't get any lower than that. And it continues to go up from there, but there is a distinct break. It doesn't exist. It doesn't have any y values between the blue and the red. And so when it stops at -5 going up, and it doesn't resume going up until after we get past -4 on the red one here, we're going to have to do two separate parts pieced together. And so these two separate parts we're going to have to do pieced together is we have to say one is y equals -5 because it's just that y value never moving. And then we have a u for the union, y is greater than -4 because it's this number and numbers bigger. Doesn't include -4 though. Once again, we went least to greatest there. Now the other way we could word this, and we doing two intervals with a union between them as well. And so we'd have one interval for -5, and we put brackets around that because it includes -5. It's the only number it actually includes here, but it is a closed circle. Union, u without a tail again, and then -4 comma infinity with -4 getting a parenthesis because it's an open circle. And so that's just telling us there's two separate parts here with a break in between them for the range, which we do see to be the case, that there is a break between these two here. Moving on to example 5. Once again, piecing together these two pieces of the function, knowing that we're split at x value of 2. So on the top are when x is less than 2, on the bottom is when x is greater than 2. So as I mentioned before, I like plugging in that actual number or where it's cut off, regardless of whether it actually plugs into that function according to this rule or not. That can help me know how the graph looks, and I'll just put an open or closed circle there accordingly. And so as I plug in 2 to this top function here, I end up getting -5/2 times 2 minus 1, and that ends up getting -6. So I end up getting 2 comma -6 as an ordered pair, and that is an open circle because this is not equal to 2, it's only less than 2. So I'm going to do 2 comma -6 as I mentioned with an open circle. Now I know that these are the numbers less than 2, so that's 2 to the left of 2 on the graph, and so I remember that my slope here is -5/2, and so I'm going to go up 5, left 2, and make a point. Noting that, hey, my b was -1, and that is where it crossed, so that's good news. Then I go up 5, left 2 again, and I could just continue doing this, but I kind of run out of room to go up. And so I draw my line, I connect these points, and I call it good. Now going on to the bottom one here, we have x plus 2. And so I plug it in there, and I end up getting the y value of 4. So it's 2 comma 4. Once again here, this is also an open circle. That's new that they're both open circles. So that's okay. We'll figure out how to deal with that in just a moment as far as domain and range go. So it's an open circle at x is greater than, or at 2 comma 4. And then my slope here is 1 or 1 over 1. So I'm going to go up 1, right 1 in an uphill manner because it's positive. And it would look something like this. And so now I piece these two together successfully. And it's okay that these happen to both be open circles because we notice that neither of these have an or equal to symbol. But as we discussed our domain, it goes forever left, it goes forever right, but it doesn't include this x value of 2. There is no actual point at the x value of 2 because both are open circles there. There's points to the left of -2, or excuse me, the point left of 2, and there's points to the right of 2, but no point at x equals 2. So how we could write this one way, apologize for that, I hit the wrong button, I meant to hit the undo button, is x equals, x does not equal, rather, 2. As long as x is anything other than 2, it's part of the domain is what we're saying. That's the only x value that's not part of the domain. So another way we could write it in interval notation would be -infinity, comma 2, with both being parentheses. That's showcasing the red part of this function. And then a union, showcasing the blue part of the function, picking up after that break of the open circles, would be 2 comma infinity. With both having a parenthesis again, just noting that, hey, it goes all the way up to 2, and then, but not actually getting to 2, and then it picks back up after 2. Once again, never actually included the x value of 2. The range here, how low does this go to how high it goes? So the lowest it gets is -6, but it never actually includes it, but it does continue to go up, up, up from there. And then here, we notice that this is actually already covered. It's redundant because that is all part of this range anyway. So we can essentially ignore that because it's just overlap. So we don't need to state it again when it's overlapping or redundant with what we already did. Whereas in the domain, these did not overlap with each other. They were not redundant with each other. So we stated each of them. And so our range here would be y is greater than -6, or listed in interval notation, -6 comma infinity, with -6 getting a parenthesis because that's an open circle there at that lowest point. Next up here, number 6, we have 3 parts of this piecewise function. How exciting, okay? So this top one here, the y value equals -1 if x is less than or equal to -5. And so when x is less than or equal to -5, the y value is -1, which is a horizontal line at the y value of -1. So I go to -5 in my graph, and I make -5 comma -1 for the y value, and it's a closed circle because it's or equal to and anywhere less, meaning we're going to the left. And now I graph that far left, the top one, in red. I'm going to graph this middle one in blue, and that's saying -x minus 3 if x is between -5 and 1. If it's greater than -5, but it's also less than 1. So we're talking about from here all the way to here, but not actually including either of those two, meaning it's going to be open circles at -5 and 1. And so 2 ways we can approach this. One, as I mentioned before, is plugging one of these in, even though technically neither one actually gets plugged in there because it's not or equal to, and plugging it in here and putting an open circle at that ordered pair. And so such, I could plug in -5, for example, or 1, either one. And so essentially I'm working my way left to right. I'll just plug in -5 here, but there's not a wrong way to do it. As I plug in -5, I get -5 comma 2. Because I'd have 2 negatives with this. I'd have negative of -5, creating a positive 5 minus 3. And so I have -5 comma 2 with an open circle being there. I note that my slope is -1, and so I go down 1, right 1 to go in a downhill manner there, all the way to +1, but making an open circle at +1 because it's not part of the answer. And had I plugged in 1, I'd have gotten 1 comma -4, which is what I see there. We also note that the y-intercept is -3, which we see here. So you also could have started at that y-intercept since it does include the y-axis or the x value of 0. The x value of 0 is the y-axis right here. Okay? And so now we go and connect these points here. And that's a new middle section of the graph, which we didn't have before because we just had a left and a right. And now we have a left, right, and a middle. And now the bottom section of the graph I'm going to showcase in green. And we're saying now as long as x is greater than or equal to 1, we're going to have, ignoring that, we're going to have the y value of 6. And so when x is 1 or greater, y value of 6, I'm going to do a closed circle at 1 comma 6. And that's just going to be an arrow going to the right here. And so now we have three different parts of this piecewise function, the top being on the left in red, the middle being in the middle in blue, and the bottom being on the right in green. Now as we piece together our domain and range, our domain here, we notice it goes forever left, has a closed circle, picks back up at the same spot with an open circle, down to here, open circle, picks back up at this spot, all the way over here. So there's no x values that aren't included. Every x value is part of this because there's no spots where there's only open circles. Every spot that has an open circle also has a closed circle, and it goes everywhere in between. And so this ends up being all real numbers again, or as we sometimes word it, or I prefer personally, negative infinity comma infinity. The range, a little bit trickier here. The lowest spot we see is right here with an open circle, and then it goes up, 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 up to here, and then picks back up after this. So we're going to have two different spots, one for the blue and one for the green. Note I left out the red, because the red here, this y value of -1 is redundant with the blue. It's already included in this section of the blue, so we don't need to list it again. And so how we list the blue section is we'd say that -4 is less than y, which is less than 2. Y is between -4 and 2, but not including either of them, so it's not or equal to either of them. U for the union, and then up here, y is equal to -6. It's just only that value, so +6. I said -6. We could also word it as two separate intervals of -4 comma 2 for the blue part, both being with parentheses because they're both open circles. Union 6 with brackets because it's only that number, and it definitely includes that number since it's only that number. And that could be our range there. Moving on to example 7 here. Once again, three parts of this piecewise function. I always start with the first part, which is the farthest left part, and then continue on to the right or down here as it goes to the middle and to the right. So on this first one here, 2x if x is less than or equal to -2. Once again, I would like to plug in this value into here, and then I can know that this is just y equals mx plus b, y equals 2x plus 0. And so as I plug -2 in there, I end up getting the y value of -4. So it's -2 comma -4. And that's going to be a closed circle because it's equal to -2 as well. I'm going to do -2 comma -4 with a closed circle, knowing my slope is +2 or +2 over 1 because this is y equals 2x plus 0. And so I'm going to go down to left 2 and down to left 2 as it goes forever left with an arrow there because these numbers less than -2. Now in this middle section here, which I'll do in blue, it goes anywhere between -2 and 4, but not including either of those numbers. And so here I'll plug in -2 here, and then end up saying that I have -1 minus a -2, so it ends up being -1 plus 2, or -1 comma, or -2 comma 1. And this is going to be up here with an open circle, knowing my slope is this -1 with the x, and so I'm going to go down and right, all the way over to 4, where there's going to be an open circle. I also could have plugged in my value of 4, which I would have gotten this value right here of -5, or I could have noted that my b is -1, which is right here as well, since this covers the y-axis or when x is 0. And I connect these dots, and now I move on to the last part in the green here. Y is -3 when x is greater than or equal to 4. So at 4 comma 3, since the y value is 3, that's just 3 forever, which is just horizontal left and right. And that's a closed circle because it's equal to 4. And so now as I evaluate my domain here, how far left and how far right it goes left forever, it goes right forever, and as we go through the graph, the only two spots we see open circles or any breaks in the graph are right here, and both of those spots also have a closed circle at that same x value, meaning every x value is part of this domain. No x values does not have a does not have an actual point here that's on the graph. And so the domain here is going to be all real numbers again, or the interval notation of negative infinity, comma infinity, both being parentheses, as infinity and negative infinity always are. The range here, it goes down forever. It does not go up forever. It stops going up here, but notice it overlaps with this one and continues going up. And so it essentially keeps going up, and every y value is covered from here down below at the bottom all the way up to here with an open circle. Regardless of the fact that it breaks here and restarts here, because these overlap with each other, where there's closed circles right here and over here, we end up having the range, the one continuous section from here to here, as well as y equals 3. Oh, my apologies, by the way. I just noticed on the green there, that's supposed to be -3, and I graphed it at +3. So some of us may have been pretty darn confused by that. So it'd be here all the way over to here. And so it's not actually two separate sections of the graph after all. It's just here all the way up to here, with these overlapping with each other. And so since those are all overlaps, we just say, okay, disregard this part where they overlap, but pick back up from here to here. And so it ends up being y is greater than, so we try that again, y is less than this highest y value of 1, but doesn't actually include that because it's an open circle. Or I could also say that it goes from negative infinity forever down all the way up to 1, and every y value is covered in between. Even if we kind of hopped around to do it, there's no y value that's not a part of this. It doesn't actually have a spot on this graph. Moving on to number 8 here, 3 parts again. So if x is less than 0, we have this top function here, negative 3x. And so as I go ahead and plot this one and graph this one, we end up having, as I plug in 0, we get 0, 0, which is just right here with an open circle. And then now as we go to the left of this, less than 0, we have the slope here is negative 3x, because this is y equals negative 3x plus 0. And so I go up 3, left 1, up 3, left 1, and this has a slope of negative 3 now, downhill from left to right for the negative. In the middle here, I plug in 0, and it is a part of this. And so as I plug in 0, I end up getting negative 1 out. And so I'm going to plot a closed circle there, because it's or equal to, and I go all the way over to 6. And so I know my slope is negative 1/2. So I go down 1, right 2, down 1, right 2, and this goes downhill, and I keep doing that over until I get to 6, where I put an open circle because it's not or equal to. And I connect those for my middle section of this graph. And then I do in the green, the very end here, x is greater than 6. And so I plug in 6 here, and as I do 6 minus 7, I get negative 1. So 6 comma negative 1. And this also has an open circle because it's not or equal to it. So 6 comma negative 1 is an open circle. And then I know my slope is a positive 1 or 1/1. So I'm going to go uphill from left to right with these spots. And now as I cover my domain, it goes left forever, it goes right forever. There's 2 spots where we have open circles or little breaks there, and one spot has a closed circle at the same spot, but the other one does not. We also have an open circle there. So x is any value except for this one right here. Oh, I went too far on my undo, so I have to redo that now. X is any value except right here. X is never 6. And we see that in our piecewise function here for our rules, that no matter what, x does not equal 6. It's less than 6 and it's greater than 6, but it's never 6 itself. So x does not equal 6. Or in interval notation, you have to do 2 separate intervals before it gets to 6, which is blue and beyond, and after it's past 6, which is green and to the right. And so that one would be negative infinity, comma 6, both being parentheses, union 6, comma infinity, just picking up right after 6. Just stating that, hey, we have it before 6, we have it after 6, but not 6 itself. the range here, the lowest it gets is here, then it goes up, 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 up with a closed circle, hops over here with an open circle, so those overlap. It keeps going up, 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 up forever. And this also overlaps here, and it goes up forever again. And so even without the red, this would be anywhere greater than this number right here down at the bottom. And now the red just kind of doubles up or is redundant on this going up forever. And so our range here is y is greater than -4. You could also write that as -4, comma, infinity, with -4 being a parenthesis because that's an open circle. Now we're going to move on to talk about something other than piecewise functions. We're going to talk about parent functions and function families. So family gives the idea of things being related to each other. And a family of functions, or function family, is a set of functions whose equations and graph all have a similar form and shape. So we have two family functions we're going to be talking about today. There's multiple family functions, but today we're just covering two of them. On the left we have these are all lines. They're all linear functions following that equation format of y equals mx plus b. Whereas on the right on number 2, these are all those v's, which we learned last section, 3.1, are part of the absolute value function family. They're all absolute value equations. Y equals the absolute value of x. Now, there's such a thing called a parent function, and this is the most basic version, or the simplest function of the family. So the simplest function of that type. So for example, a parent function of a linear function is just y equals x. This is where the slope is 1 and the b is 0. It's the most simplest version where we have no other adjustments to it. And so we have our b at 0 and our slope of +1, where we're increasing at 1/1 for our rate the whole way through. And also decreasing at 1/1, which once again going uphill from left to right the whole time. Whereas absolute value, our most basic version, is y equals the absolute value of x. Now we could also word this as f of x in either of these. So if I wanted to, I could write f of x here. And that's often a way it's written as well. It's how we wrote it before in last section when we wrote the absolute value. We did I did more than I wanted to there. We did f of x equals absolute value of x. And as I've stated multiple times, y and f of x are the same thing. So either way you do that is perfectly fine. Now the absolute value function there would end up looking like this, a v with the vertex at 0, 0, and just continuing on in each direction forever and ever and ever and ever, as such. And you could plug in all sorts of x and y values to go through that and plot those points if you wanted to. Now we have transformations that alter or change the parent function to make them more complex. And we've graphed tons of these. We graphed tons of linear equations and absolute value equations from last section as well that have these different types of transformations on them. Now here it says that we're going to use the calculator to graph these and compare it and give a brief description. Instead, I'm actually going to have us skip this for a moment on 3 through 9 and come back to that after we learn more about what these transformations are, and then do it from the equation rather than doing it from the graph. So let's first talk about 3 types of transformations we can have. So the first type of transformation is a translation. And this is not changing languages like from English to Spanish or vice versa. Rather, it slides or shifts a function. Think about it as you're clicking and dragging it, like you're moving a picture or something like that around on a document. You're just clicking and dragging it over. You're not changing the size of it. You're not changing the rotation of it or anything like that. You're just moving it to a new spot. It's also kind of similar to like a cut or a paste, to where nothing changes about the function, nothing changes about the picture, except for the placement of where it is. The second type of transformation we have is called a dilation. a dilation. And oftentimes when we think of the word dilating, we think of eyes dilating. The pupil dilates to let more and less light in, depending on how much light there is in the room. And so that's just increasing and decreasing in size. So it stretches or compresses the function vertically or horizontally. We're only going to be talking about vertical stretches and compressions here, but it stretches it vertically here or compresses it vertically down. And then our third type of transformation is a reflection. And a reflection means it mirrors it or flips the function. And we're going to be talking about vertical reflections that are done across the x-axis. And you might be confused, well, Mr. Crossley just said vertical, but he also said across the x-axis, and they're the same thing. And they are the same thing, which we will see, which we will be seeing in future sections. Now, moving on to this next page here to talk about the rules for these transformations. So we can tell the transformation that's happening without even looking at the graph. And how we can tell it is based upon these different rules. Okay, so we have 4 different ones for transformations, and these are 2 sides of the same coin for this and 2 sides of the same coin for this. They're just related. And so when you have x plus h, notice here, h is just going to be a number, as well as k being a number, as well as a just being a number. They're all just numbers, whereas x is our normal x. Now, if you have x plus h or x minus h, note that the h is in the parenthesis with the x, where here the k is out of the parenthesis. This is what we call a horizontal shift, a shifting left or right, or horizontal translation or slide. Whether you say shift, translation, or slide, they're all really the same thing. I like to use the word shift personally, so that's what I write. Once again, a shift, slide, or translation are all the same thing. So this shifts, okay, shifts the function left. It shifts the function left h units. So whatever the number is. So if h is 3, it shifts it left 3 units. If h is 5, it shifts it left 5 units. And so here, you might be wondering, Mr. Kossel, it says plus, and plus on left and right means that we go to the right. So why is it saying left, okay? And that's actually not a mistake. That's very purposeful. And the best way I can describe this is by telling you that this number is going to be a liar every time. It's kind of weird to say, I know, to call a number a liar, but that number is always going to be a liar. So if we see a positive there, we're actually moving left. And if we see a negative there, that means we're going to be moving right. So this shifts it right h units. So this h value, I should say, this h value is a liar. It tells us we're shifting left to right, but it's the exact opposite of the direction we think it would go. When it's plus, we think it'd go right, because once again, that's positive on the x-axis. However, it goes left. And when it's left, we think it might go. When it's negative, we might think it goes left, because that's left on an x-axis is negative, but it actually goes to the right. And now with the translation here, for this one with k, when it's outside this parenthesis, you know, the parenthesis closes here, this is going to be a vertical shift. So this is going to shift it up k units. And this one is true to what it looks like, where plus for up and down we think of up, and it does go up. And minus then would mean that it goes down h units. So notice this one is not a liar. This one is very straightforward. Only the h is our liar. That's the one that does the opposite. The h value always does the opposite of what it looks like it's going to do. But the k value does exactly what it's going to do. Positive does go up, negative does go down. Next here, a dilation. Actually, before we go into that one, I want to go back to the previous part here and have us go over these that have the translations, aka 3 through 6. And so notice on 3 and 4 that the plus or minus 2 is inside the absolute value, whereas on 5 and 6 the plus or minus 2 is outside the absolute value. And that's because 3 and 4 would follow the first 2 examples from the page we were just on, where it goes left and right, whereas on 4 and 5, or excuse me, 5 and 6, it's going to be the up and down there. So on number 3, the absolute value of x plus 2 means that this shifts, translates, or slides, any of those 3 words, left 2 units. Or you could just say slides left 2 if you wanted. And that's because, once again, this positive is really a liar. It does the opposite. It moves it left, that number. And then number 4 then means that it's going to be shifting it right 2 units. Or shifts right 2. Once again, you can also say translates or slides there as well. Now on number 5 then, this is telling us going up 2 units. So it shifts, translates, or slides. Once again, I like the word shifts the most personally. So it shifts up 2. Whereas on number 6, this minus tells us it's going down 2. And I want to once again note the difference that when the number is adding or subtracting with the x inside the absolute value, it ends up being horizontal left and right. But when it's outside the absolute value, it's the y value up and down as that's changing. Now, even though here we saw parentheses, and on the other side we saw absolute value, it affects that, as far as the translation, the exact same way regardless. Next, we're going to have dilations. So a times f of x on both of these, and when the absolute value is greater than 1 versus the absolute value being less than 1. And that just means absolute value is greater than 1, meaning it's a number such as 1.2 or 3 or 4, the number is greater than 1, or less than negative 1. Okay, so it's not between negative 1 and 1. It's not a number smaller than 1. And so when this happens, this is going to vertically, aka up and down, vertically stretch by a, whatever that number is. Whereas when a is less than 1, the absolute value of a is less than 1, such as 1/2 or 3/4 or 2/3 or negative 2/3 or negative 3/4 or negative 1/2, this would be a vertical compression. So this is vertically compressed by a. And so here we don't have to worry about an inside or an outside of this one. It's only outside parentheses here, just kind of like these two were outside the parentheses, which is why it's a vertical thing up and down, similar to how this was vertical up and down. And so now let's go back to this slide here and talk about it with absolute value functions on 7 and 8. And so on 7 here, this is a 2 outside. On 8 here, it's a 1/2. Now 2 is greater than the absolute value of 1. The absolute value of 2 is greater than 1, I should say. And so the absolute value of a. And so this is a vertical stretch by 2. Whether you say vertically stretch or vertically stretches or vertical stretched, vertically stretched, however you word that, as long as you have the word vertical and the word stretch, I'm kind of happy with that. And tell us that it's by 2 because that's the number. If it was a number 3, it'd be by 3. If it was a number 4, it'd be by 4. And then number 8 here, because 1/2 is smaller than 1, the absolute value of 1/2 is less than 1. This would be a vertical compression. And then by whatever number this is, in this case, 1/2. And then our last one we're going to be talking about here is the reflections. So the reflections here, we have a negative out in front, and this reflects it across the x-axis, aka a vertical reflection. Let me showcase why that'd be a vertical reflection here. Note here that if we have some sort of graph here like this, I'll do a quadratic graph there just for a moment. If I reflect it across the x-axis, that means the new image is going to be like this, and that is a vertical reflection here because everything's just mirrored from here to here across this x-axis. If we just folded it down, you could think. And so now let's showcase that on our last example on the previous page, example 9 here, where we have negative absolute value of x. And so this just reflects across the x-axis. Or you could also call it a vertical reflection. It's the same thing. Alright, now let's apply this a little bit more here. So we actually already practiced a little bit of this on those last few examples. So hopefully you can try some of these on your own, pause the video and try that, and then continue the video and try these with me. So describe how these functions compare to the periodic functions, aka what translations, dilations, or reflections happen here. So on number 10 here, this minus 3 is occurring outside the absolute value. So because it's plus or minus, is adding or subtracting, we know it's a translation. Translation always deals with adding and subtracting, like we saw up above. All the ones that added and subtracted, note that these was adding or subtracting. So actually I'll just write add / subtract. We're subtracting 3, so it's going to be a translation. It's a vertical translation because this minus 3 is outside of the absolute value. And since it is vertical, it does exactly what it says. In this case, going down for minus. So this is a shifting or vertically or translation or slide down by 3. Number 11 here, we see plus 7. Once again, we're adding or subtracting, so it's a translation, slide, or shift. And this time it's inside the absolute value, so it's horizontal left and right, which means we do the opposite of what it looks like. So since it's positive, we think it goes right. However, the opposite of that is negative. Remember that number's a liar there is how I like to joke about it as well. And so it shifts. If I could write an H there, if it didn't glitch out on me. It shifts left 7. Now on number 12 here, we have two different things happening here. So we have this minus 4, which tells us that it's shifting right, because it's the opposite, and it's inside, so it's it's left and right, and then it makes it the opposite here. And then it also has out here this minus sign, and that minus sign, we're told, reflects it. Okay, so two different things, and I don't care the order you list it in. Typically, we just go left to right for the transformations we see. Once again, I don't care the order you list these in. So one is that it has a vertical, try that again, not a vertical. It has a, I guess you could call it a vertical reflection, or reflects across the x-axis. And then the other thing it does is it shifts, slides, or translates right 4, because once again it's the opposite of what we see there. So two different things, and there's no correct order for that. Once again, we typically just go left for right for how we see it. So the minus, the negative there that reflects it comes first from left to right, so I typically just write that one first. Once again, not right or wrong, the order you put those in. Number 13 here, once again, two transformations happening here. This 4 outside multiplying. Multiplication is associated with the dilation there. Okay, so up above we had that the translation was addition subtraction, so dilation is multiplication. And so we are vertically stretching. It's a stretch because it's greater than 1 or less than negative 1. Either one, the absolute value of 4 is greater than 1. So it vertically stretches. So a vertical stretch by that number by 4. And then this one here, it's plus, so it's dealing with a shift or translation or a slide. And since outside the absolute value, it ends up being a vertical one. And so it does exactly what it says to where it goes up. So it goes shifts up 1. Now on number 14 here, we have f of x equals 1/3 x. And so this is the only thing happening to it. The absolute value of that is less than 1, meaning it's a compression. So it's a vertical compress or vertical compression by 1/3. You can also say vertically compressed. I'll accept really any tense of the word. Number 15 there, we have two things happening. One is these addition of 2 and one is a subtraction of 5. The addition of 2 happens inside the parentheses, or inside the absolute value bars, I should say. And so that means it's a horizontal left and right. And so this is shifting, translating, or sliding. And the direction it's doing that is opposite of what we think it would since it's horizontal. So it's left since it's positive. So it shifts left 2. And you could say also and down 5. This is also a shift. And since it's outside the absolute value, it's vertical, which means it does exactly what it says it should of -5. Now you can split that up into 2 different lines of shifts less 2, shifts down 5. Or you could say, since they're both shifts, that we can just combine it into one like I did here, where we say it shifts left and down by the 2 different numbers, specifying each number. Number 16 here, we have 3 different things it's doing. We have this negative here, which does one thing, this 2 does another, and this -1 does a third thing. So just going in order is what I typically do. The first thing it does is it reflects. It reflects, you could just write reflects, or vertical reflection, or reflects across the x-axis. The next thing it does is this 2. The absolute value of 2, or the absolute value of -2, is greater than 1, meaning it's a vertical stretch. So it's vertical stretch by 2. We'd leave the negative off because that just meant that it reflected it. And then this last one here, the -1, is inside the absolute value, so it's the opposite of what it says, and so it's going to go right, so it shifts right one. On to 17 here. We have 4/3 and this 2, so 2 different things going on here. This 4/3 is telling us it's a vertical stretch because the absolute value of 4/3 is greater than 1, so that's a vertical stretch by 4/3. And the next thing is telling us that it's a shift, translation, or slide because it's adding. In this case, it's vertical because it's outside the absolute value, and so it's going to be exactly what it says it's going to do, so it's going to go up, so it shifts up 2. Now we're going to close out this very long section by writing the translations going the opposite direction of what we just did. So here in examples 10 through 17, we practice being given the equation or function that's been modified or transformed, and then saying, hey, here's what happened to it in order to get there. Now we're going to go the other way around. We're going to go saying, hey, we're told this is what happened, and now we're supposed to write the absolute value function. So translated 6 units right. So once again, knowing the normal absolute value function is f of x equals absolute value of x. We're going to have f of x, and we're going to have f of x on all of these. So get used to writing that. If you want to write y instead, that's perfectly fine. You could also write g of x for all I care, or h of x, or whatever, but get used to writing that. So I just went ahead and wrote it there, knowing that I'm going to have it on every single one of these. So 6 units to the right. So since it's translated, we're adding or subtracting, and since it's horizontal, right or left, it's going to be inside the absolute value. And since it's horizontal, it's going to be the opposite of what I think. So right I associate with positive, but it's actually going to be -6. Number 19, reflected in the x-axis, reflected across the x-axis. It's weird that it says in there. It really kind of should say across. In doesn't give the right idea. It's across the x-axis or over the x-axis, but that's going to be the negative outside, and then it's translated 2 units up. So this tells us there's a negative. This tells us it's adding 2 at the end because it's up for a translation, and so it's outside the absolute value. So we're going to have a negative outside the absolute value to begin, absolute value of x, and then a +2 at the end because vertically it goes outside. Number 20 here, we're going to have vertically stretched by a factor of 5. That's multiplying by 5. Then translated 1 unit left. It's going to be inside the absolute value, adding 1. And so this is 5 times the absolute value of x plus 1. Remember that horizontal translations do the opposite of what we think they do. for the equation. Now here on 21, we're going to translate 3 units right and 4 units down, so 2 different translation. So this one, a horizontal one's inside the absolute value and does the opposite of what we think, so a -3 for going right, whereas the other one is vertical, so it goes outside the absolute value and it subtracts by 4, because it does exactly what you think it would by subtracting to go down. It's going to be the absolute value of x minus 3 minus 4. Next here on 22, vertically compressed by a factor of 2/3 and reflected up in. Once again, I like the word across more there, or over. I think it makes more sense grammatically speaking. The x-axis. And so this tells us the negative, and the vertical compressed tells us it's multiplied by 2/3. And so it's 2/3, but a negative 2/3 times the absolute value of x. They both get applied outside or before the absolute value. Next up, number 23. So we're vertically stretched by a factor of 2, so that tells us we're multiplying by 2. And then we're also doing translated 9 units down. Don't be confused about the whole then aspect. The order that these are layered in are not going to impact us in this class at all. So it's vertically stretched by a factor of 2, then translated 9 units down. That means -9 outside the absolute value. And so it's going to be 2 times the absolute value of x minus 9. Remember, a vertical translation happens outside the absolute value, and is straightforward with what it says. It doesn't have to be opposite. It's a liar, like the what h is with the horizontal translation. Then on 24, here our last example for the lesson. Vertically compressed by a factor of 1/4, meaning we multiply by 1/4. Shifted 1 unit left, so since we're shift, translation, or slide, we're adding or subtracting. Since it's horizontal, it goes inside the absolute value, and it does the opposite. So 1 unit left really means +1 inside the absolute value. So it's 1/4 times the absolute value of x plus 1. And that wraps up Algebra 1, or excuse me, Algebra 2, Section 3.2.